For all of history, gold was the standard of wealth. In many great empires, gold was the most valuable resource that a single person could own. Its low quantity, metallic shine, and enduring durability make it a prize for humans throughout history. Even today, gold remains a symbol of wealth and prosperity and a major driver in the world economy. But within the atoms of gold lies billions of years of cosmic evolution, forged from the heart of massive stars long before Earth was created. This is the story of gold, from the great stars of the night sky to the rocks of Earth. Stars like our Sun may look like forges for gold. They have hearts of elementary molecules that burn anything they touch. But these stars cannot create gold. To create such elements, something far more extreme must occur. Enter the neutron star, a stellar object born from the death of a massive star, packed so dense that a single teaspoon of its material would contain more mass than the planet Jupiter, and glowing with temperatures that far exceed our Sun. When two of these great objects collide, or when a supernova occurs, the conditions become extreme enough to create atoms of gold, platinum, uranium, and others, scattering them across the cosmos. As these atoms drift through the universe of millions or even billions of years, some would drift to a newborn star system, one that we know too well. And that is our own solar system. When the planets started to form, these atoms would become infused in their cores and surfaces, giving each planet the essence of neutron stars. But these atoms do not just appear out of nowhere. To fully understand how gold and other elements are created, we have to journey to the moment before a supernova occurs. During the final years of a supermassive star, its fuel exhausts, which leaves it vulnerable to the effects of gravity. When gravity wins against the outward pressure coming from the star's core, its outer layers are pushed inward, causing unimaginable pressure and heat. At this moment, neutrons flood the extreme environment. The neutrons become captured by the nuclei of the surrounding atoms in a process called the rapid neutron capture process, or more simply, the R process. In just a few seconds to a few minutes, the nuclei in the core build up larger and heavier elements like gold, uranium, and platinum. Just like supernovae, during neutron star collisions generate extreme heat and pressure. The two neutron stars spiral toward each other, unleashing energy far greater than what any normal star could produce. Their extraordinary densities amplify this energy, creating a vast, destructive field of plasma. And with these extreme conditions, gold and the other elements would form and be blasted to the depths of the universe before reaching planets like ours. With millions of neutron stars across the entire universe, it seems like common sense that there would be an abundance of gold across the universe. But that is not true at all. When supernovae occur and neutron stars collide, the amount of gold created is very little compared to the amount of matter released during these events. For perspective, a single neutron star collision can produce a moon's worth of gold, while a larger collision can produce Jupiter's mass in gold. From our knowledge, supernovae produce very little gold compared to the collision of neutron stars. And because neutron stars are already so rare, this makes the probability of collision very low, occurring in great and vast nebulas that have many stars. This scarcity explains why gold is very rare and makes it seem wondrous that we are even able to obtain on Earth. As the gold reached our early solar system, most of the gold sank into each planet's core, hidden from view for billions of years. On rocky planets like Earth and Mars, some became littered across the planet's surface. On gas giants like Jupiter and Saturn, the gold became trapped under a deadly layer of toxic gas, inaccessible for anything. Meanwhile, moons and asteroids preserve gold and the other elements under a thick layer of ice and rock, waiting to be released once it reaches a planet. In our current age, scientists are trying to extract and find gold and other precious metals from asteroids and even other planets. We have one big mission that is setting off to find these rare materials. This is NASA's Psyche mission, bound for asteroid 16 Psyche. As of 2025, Psyche remains a major focus for the future of asteroid research. Its origins remain mysterious, but scientists still have an explanation for what happened. Almost 4.5 billion years ago, when the solar system was still forming, protoplanets that would one day be Earth, Mars, Saturn, and Jupiter would orbit a newborn sun. One of these was Psyche, which pulled in metals, silicates, and other types of debris into its center. The heavier and denser metals would gravitate to its inner levels and form a metallic core. The lighter silicates and metals would form the rocky mantle and crust that would become the planet's surface. It was set to be a small rocky planet, just like Mercury or Mars, but it would soon face a violent end. Possibly around a few millions of years after the formation of the solar system, Psyche would face a large impact from another stellar body. The energy created by this collision would be powerful enough to blast away the protoplanet's rocky outer layers, stripping it down to the dense metal core that would remain for billions of years. Over time, the newly formed asteroid would drift to the asteroid belt, where it would reside for the rest of its lifespan. Today, Psyche is a major focus for the scientific community. The fact that it existed for the entire lifespan of the solar system gives us a window into planetary formation. And that is what the Psyche mission is trying to find out, along with extracting samples of precious minerals. When the mission launched back in October 2023, it became a highlight of the space community. NASA marked out one mission goal to drive the entire program. The goal is to study the asteroid's nickel-iron core that contains a substantial amount of gold and prove that it is the metallic core of a protoplanet. In particular, estimates of its gold value reach up to the hundreds of billions of US dollars. When the spacecraft reaches the asteroid, it will deploy probes that determine the exact composition of its core and its age. It will achieve this by using a gamma-ray and neutron spectrometer, or GRNS, magnetometer, multispectral imager, and X-band radio telecommunication system. The GRNS will detect gamma rays and neutrons coming from the asteroid using gamma-ray spectroscopy. The process begins with a supercooled, high-purity germanium detector. When a gamma ray hits the detector's crystal, it dislodges the electrons. Because the number of electrons released is directly proportional to the energy of the gamma ray, it produces a distinct energy signal that is converted to an electrical pulse. This pulse creates a spectrum that is used to identify the specific elements in the surrounding ground. The magnetometer will detect the magnetic field left behind by the protoplanet. The system uses two twin-flux magnetometers that separate the asteroid's magnetic field and any other stray magnetic fields. Each of these sensors detect the strength and direction of the magnetic field by using ferromagnetic cores that respond to the field. These changes create voltages that are converted to electrical signals, allowing scientists to measure magnetic variations in specific parts of the asteroid. If the asteroid is truly magnetic, then the gold and other metals would be dispersed across the different layers. The multispectral imager detects subtle differences in material composition. It uses light from the sun that reflects off the asteroid's surface and enters the camera. The light is then processed by a computer that detects specific wavelengths of light indicating specific metals. It then gives a detailed map of the asteroid's surface, which we can use to better understand this stellar object. And finally, the X-band radio telecommunication system uses high-frequency wavelengths around 8 to 12 gigahertz that are sent to Earth. Scientists then identify the small changes in frequency, also known as a Doppler shift. These shifts are used to calculate and determine the asteroid's mass distribution, which allows us to understand its interior composition and even detect traces of gold and other rare metals. Together, these four instruments make the Psyche spacecraft the perfect tool to reveal the mystery of Psyche's origins and better understand how metals are distributed in our solar system. From the heart of a dying star to our scrambling hands, gold has traveled billions of years across the cosmos, landing on planets like Earth. So when you hold a piece of gold in your hands, just remember the great adventure it went through to end up there. Thank you for watching the story of gold. If you have reached this far into the video, thank you so much for watching. Please subscribe and like the video. It really means a lot. And as always, thank you so much for watching.